Hi everybody, and welcome to example 1. We are looking at page 61 on the workbook here, and this is another example of a slope field, our second example of that. We're just going to be looking at parts A and B of this problem in this video, and then saving part C for a little bit later on in this section. Okay, so let's read this together. So P of T is representing the population of a bacteria colony after T hours. Okay, and we'll assume that the population is modeled by the differential equation dp dt equals 0.3p. And that's just a way of communicating some information about how fast the population is growing. And they're giving us a slope field. Okay, so a computer has generated the slope field for that differential equation. Okay, so if we look at part A here, they'd like us to draw in population functions that are solutions to the following initial value problems. Okay, now that's kind of a new term. Okay, initial value problem is just a fancy way of saying a differential equation together with a starting condition, an initial condition. Okay, and I'm going to remind you kind of what this notation means. So the 0 that you see here, that's a value of time, our input variable, and then 100, that's a value of population. So in number 1, they're basically telling us, assume that we start with a population of 100 bacteria. Okay, let's see if we can draw that curve in our slope field. So we need to first find the point 0, 100. Okay, that's going to be here. And again, the idea of a slope field is it gives us information about how quickly our function is changing. Okay, so think of every line that you see in the slope field as a tangent line. And we want to draw our population curve so that its slope matches the slopes of these tangent lines as we draw it. Okay, so we start out with a slope about like that, and then just doing your best to kind of match the slopes kind of as you're drawing the curve. Okay, and I see I'm not doing a very good job here, so let me try again. Okay, and just do the best that you can. We're just trying to match the slopes as best as we kind of work our way through the field. So maybe something like that. Okay, so roughly speaking then, that curve that we just drew is what the population function would look like, roughly, if we started with a population of 100. And we can see that it increases and it's concave up. It gets steeper as we go out because our slope field lines are getting steeper. All right, now how would that be different for part 2 here? Well, the only difference is that our starting population is different. This time we're going to assume that we start from 200 bacteria. Okay, do the same thing. This time we sort of start out with a steeper slope. Okay, so our curve is going to start out increasing a little bit faster than it did before. Okay, and we get a population curve that maybe looks about like that. Okay, and again, these two curves that we drew represent qualitatively what the population function of the bacteria would look like. Okay. So let's move on to part B, see if we can answer that. And this is kind of an interesting question. It would like us to estimate the amount of time that it takes for the population of the bacteria colony to double if it starts with 200 bacteria. Okay, how do we answer a question like that? Okay, well, one kind of hurdle we need to get over is which curve do we want to use here? Okay, we've got two curves that we drew. Notice that the key is this condition here. They tell us that we're talking about a bacteria colony that starts out with 200 bacteria. That matches the second curve that we drew. That's the one that had a starting population of 200. Okay, so here's my question to you. If we start with 200 bacteria, what would double 200 be? Okay, it would be 400, and it's just asking us how long does it take for our curve to increase from 200 to 400. Okay, well, we can answer that graphically by just finding the point on the curve that goes with 400 bacteria and then just asking, what approximately is the time that went with it? Okay, somewhere down there. And this is a very rough estimate. You may have drawn your curve, it might look a little bit different, and so you might have your t value occurring at a different point. But what would you guess that that number is about. Okay, I'd put it maybe at about 2.2, somewhere between 2 and 3 for sure. Okay, so we could say it this way. It takes about 2.2 hours for the population to double. Again, you did this, you may have very well gotten a different number than I did. It's not an exact science here, but it gives us a rough estimate of how long it's going to take for the population to double